Alright guys, in this problem we're gonna review projectile motion. So this problem is from your textbook. This is problem 55, chapter 4. It says that you are 6 meters from one wall of a house that you see in the picture, and you want to toss a ball to your friend who is 6 meters from the opposite wall. So you can see in the picture that the house is 6 meters wide, and you are 6 meters away from the left wall. Your friend is 6 meters away from the right wall. The throw and the catch each occur 1 meter above the ground. So with this information, we're looking for the minimum speed that would allow the ball to clear the roof. And we also want to know at what angle should the ball be tossed. So let's start by drawing a picture. So this line there represents the height of the house from the ground level to the top of the roof. The picture shows us that the roof is 3 meters above the ground. We also know that the house is 6 meters wide, which means that the left section of the roof is 3 meters wide. And since the angle is 45 degrees, we know that the roof must be 3 meters tall. So that gives us that the height of the top of the roof is 6 meters above ground level. So this is going to be important information. Now consider that the ball is launched from a point 1 meter above the ground, and it is caught 1 meter also above the ground. So let's simplify our little sketch here. The height, therefore, from the launch point to the highest point of the trajectory of the ball should be 5 meters, and at that point, at the highest point of the parabola, we must be 9 meters away from the launch point. Notice that is 6 meters to the wall and then 3 more meters to the middle of the house, so a total of 9 meters in the x direction. So we have a parabola that has the highest point is 5 meters above the ground, and that occurs 9 meters from the launch point. This information should be enough to allow us to calculate the two things that we're looking for in this problem. The first one is, what's the speed of the ball? It says the minimum speed, so that is the minimum speed will be the speed of the trajectory that just touches the top of the roof. Okay, so assuming that the trajectory, the parabola that the ball follows has a height of 5 meters, that tells us that is using the condition that we're talking about, the minimum velocity. So we're looking for that minimum launch speed, V initial, that I call there. And the second question is, at what angle do we need to toss this ball? So for projectile motion problems, you're always going to write down the 4 equations that apply for projectile motion. The first 3 apply for the y component of the motion. It's always referring, those 3 first equations are always referred to the y component of the velocity and position and acceleration. And the fourth one is the one that has to do with the motion along the x direction, which hopefully you remember that in the x direction, a projectile does not have an acceleration. It will have a velocity, but not an acceleration. So that results in delta x equals vx times delta t. So using these 4 equations, you can solve any projectile motion problem. So let's start by choosing a final point. We have an initial, clearly, where the ball was launched, but the final point, I'm going to choose it to be at the top of the parabola. And the reason why I'm choosing that point is because I know information about that point. I know that that point is 5 meters above the ground. I know that point is 9 meters horizontally, 9 meters away from the launch point. So you want to pick the final point, the place where you have information about the motion of the ball. So that's my final. So the first equation that I can identify here, where I know a bunch of things and there is only one unknown thing in the equation which I can solve for, is equation number 3. At the final point, the velocity of the ball must be horizontal, otherwise it won't be the top of the trajectory. So we know that the vertical component of the velocity is 0 at that time. The y component of the initial velocity will be interesting to know. It will help us to we will be using that to find the speed of the ball at the beginning. This will give us the y component of the velocity of the ball, And in that equation, we know g, of course, and we also happen to know delta y. We know that the final point is 5 meters above the initial point. So this is an equation that has an unknown, and everything else is known, so that equation will give us the y component of the initial velocity. So if we replace on the left hand side, that's a 0, right hand side vy initial square minus 2 times 9.8 times 5 meters, which is the height of the final point. You replace those numbers and you solve for the y component of the initial velocity. So the y component of the initial velocity, of course, is related to the final velocity, to the initial speed of the ball, which is what we're looking for. So we're halfway there. The numerical answer for that is 9.89 meters per second is the initial vertical component of the velocity. Now we need to find out how much is the x component of the velocity. That way, once we know the x component and the y component of the initial velocity, we'll be able to tell what was the initial speed. That's one of the things we're looking to get in this problem. So now we have to focus on finding a way to calculate the horizontal velocity of the ball, which is, as you know, constant. The horizontal velocity is constant because the acceleration in the x direction is 0. The only equation that has velocity in the x direction is the fourth equation. In the fourth equation, using the same initial and final points that we used before, we have that delta x should be 9 meters. Vx is unknown, and we don't know how much time it takes the ball to go from the initial to the final point. So it seems like what we have to do now is figure out how much time it takes the ball to get to the top of the parabola. Once we know that time, the fourth equation gives us the x component of the velocity, and with that x component and the y component calculated before, we got the speed using Pythagoras theorem. So let's do that. How do we find the amount of time that it takes for the ball to reach the top of the parabola? What is the time to get to the top? So is there an equation that gives us this amount of time? So equation number 1 is going to give us that, because in equation number 1, at the point that we marked as final, again the velocity vector is horizontal, so the Vy final is 0. So in that equation, the left hand side is 0. The right hand side, Vy initial, we know it, we just calculated it on the left hand side of the screen. We got that. G is 9.8, delta t is what we're looking for. So replacing 0 equals 9.89, which was the initial vertical component of velocity calculated before, minus 9.8 times delta t top. That gives us the time to get to the top. So solving for time, we get 1.01 seconds to get to the top. So how is this time important? We just said that equation number 4 right there, equation number 4, can allow us to calculate the x component of the velocity. So we're going to replace in that equation delta x equals 9 meters. We're going to replace that it took 1.01 seconds to get there and solve for Vx. So Vx is going to be delta x over delta t. So that is 9 meters divided by 1.01 seconds. And that gives us 8.91 meters per second is the x component of the velocity of the ball, which is always the same. It's the velocity in the x direction is constant. So we got these two numbers. One is the y component of the initial velocity, the other one is the x component of the velocity. So they are the components of the initial velocity. And to find the speed, the initial speed, which is what we call Vi, then we do Pythagoras theorem. I'm rounding 9.89 to 9.9 and rounding 8.91 to 8.9. So to two significant figures, we get that the answer, well, this one's 3, but anyway, 13.3 meters per second is the initial speed. Okay, so that answers that question. What's the minimum speed to have the ball clear the roof? The second question was, what is the angle at which we need to launch this ball? So the launch angle is the angle formed by the initial velocity vector. The angle that a vector forms can be found by doing the inverse tangent of the y component of the vector divided by the x component of the vector. So Vy initial divided by Vx. So we do inverse tangent of 9.89 divided by 8.91, inverse tangent of that, and that gives us the angle, which turns out to be 48 degrees. So we have found now the minimum speed and the angle at which to launch this ball, so that the ball just barely touches the top of the roof and goes to the other side and is caught by your friend. Alright, so this is a example of a projectile motion question.